Hi, today's lab is about the specific heat. Now this sheet is on canvas for you to print out and fill out as I go through the experimental part of this video. I will be measuring the data, showing you the measurements and the procedures, of course, observations, and you will record all of that on your sheet as you watch the video. And then you will go through and answer all the questions. Of course, you can answer the pre-lab questions first, and then watch the experimental sections, and then go through and answer the questions dealing with the experiment and the post-lab questions. Now, if you can't print this out, you don't have a printer handy, you can write this out by hand. I mean, write the answers out by hand. You don't have to rewrite the questions. If you want to rewrite the questions, that's okay, it's up to you. But you could just number it, with the appropriate title on your notebook paper and write out the answers to the questions. And for the data tables, you can make your own data tables by hand on notebook paper. Again, if you don't have a printer handy. Of course, it's a lot easier if you have a printer, then you can just fill it in, and then either way, you're going to need to photo or copy, scan in the answers to all the questions and all the data that you filled in. You have to scan all of that in some fashion and send it to me, preferably in the drop box that I'm going to put on Canvas for your labs. Each one will be titled accordingly, like the one for this week is the specific heat lab, and so you will put up, or you'll load up all of your answers and data records as a nice convenient file on Canvas for me. If you can't submit it on Canvas for some odd reason, then you can email it to me, and that's fine as well. Just the more convenient, the better. PDF files are probably the easiest thing to do. So on to the business here, though, of the day, which is talking about specific heat and showing you some examples that you will be able to use for your own problems, okay, or the problems in the lab here, and apply them to other material in the rest of the class, hopefully. So I like to say, what is specific about specific heat? So specific heat is specific to a specific substance. That's what I like to say 7 times fast, and try not to stand too close to anybody, especially in the day of germophobia, which we're experiencing. And don't say this 7 times fast, or say this too much, because spittle is everywhere. It's just crazy. You need your safety goggles, face mask, and everything else, because specific heat is specific to a specific substance. Now, what does that mean? It is the amount of heat required to raise a gram of that material 1 degree Celsius. That is the specific heat. We can actually write on the board here. You ready? All right. First thing, writing on the board. So hopefully you can read this okay. I'm going to try to write nice and big. So the specific heat is specific to a specific substance, and it is, let's define it as a big capital S. S. Makes sense. Specific heat. S is equal to, well, the amount of heat. What's the units on heat? The units on heat is calories. That's the unit of choice that we're going to use, calories. Little calories for starts. That's what's convenient in our lab where we're working on a small scale, convenient scale. So calories, that's the amount of heat required to raise 1 gram of substance. That's like saying calories per gram. So calories required to raise 1 gram of substance, 1 degree Celsius. So that's calories per gram per degree Celsius. That is the fundamental definition of specific heat. Well, take a metal, like we're going to use today, aluminum, and look at its value for the specific heat. And it's, well, you can look at the table here. The table in your sheet here says aluminum is specific heat, or has a specific heat of 0.215. That's calories per gram per degree Celsius. Well, if you look at a different metal, copper, for instance, well, it's 0.092. That's a big difference. And so no two pure substances have the same specific heat if you get enough significant figures. Usually 3 significant figures is plenty to distinguish between the substances. So it can be used to uniquely identify the material, similar to density. The last lab we did before spring break was on density. And if you know the density of a material, a pure substance, to enough significant figures, you can uniquely identify that material just based on that density value. That's called an intensive property. An intensive property helps you to uniquely identify the material, as opposed to an extensive property, which depends on the amount of the material. Well, specific heat does not depend on how much of the material you have. You could have a huge block of metal or a little bitty sample of metal. It's going to have the same specific heat. That's what is unique to that type of substance. So now I want to go over an example problem on the board of the main types of calculations you'll need to do for this experiment. There is example problems in the photocopies, very helpful problems that you need to look over and read and understand. The copies that have this formatting, you know, that look like this with the way everything is organized, have a very good introduction, background, highly useful to tell you what's going on with the experiment and fill you in. It's pretty well self-sufficient, self-contained. If you understand what's in the background, you can answer all the follow-up questions fairly well. And so there is an example problem that is given in here that is just like the type of data I'm going to be gathering in the lab today. And if you read through that example problem and look at how it's worked out on the next page, you should have a good understanding of how to go through the calculations with the data that I'm going to gather for you to watch, okay? However, I still like to go over another example problem. So for a second one for you to have and to make your life easy, this will count full credit for you. It's kind of free if you copy everything that I put on the board nicely onto number 4 here on the pre-lab assignment. You'll get full credit for it. So I'm going to write it out, the entire problem, or the solution to the problem, and all you need to do is write it in your own paper, and that way you can get a freebie on your solution here. I also wanted to point out real quick while I'm thinking about it, something that people may need to know or be sure on is number 3 says how much heat is lost by a 30-gram sample of iron. Well, heat is different from specific heat. Heat is also different from temperature, okay? Temperature is a component of heat, one might say, or it's, you know, directly dependent on heat and vice versa. But they're not the same thing. Temperature, of course, is measured in units of Fahrenheit, Celsius, and Kelvin. Heat is measured in units of calories, which is what we're going to use in our lab, and, calories and joules are the 2 most common ones. BTUs, British thermal units, are also another common unit that you may run across dealing with heat. Now, so when it says on number 3, how much heat is lost, it's asking how many calories is lost, which is a big part of our lab, figuring out how many calories is exchanged from the metal into the calorimeter. That's what the lab is all about, is calorimetry, or how to do calorimetry, basic calorimetry. And the purpose of it is usually to find heat that is exchanged. And so the metal is losing the heat, the calorimeter, or the water in the calorimeter, gains the heat, and that's what we're going to show in a minute on the board here for the example problem. Now, I wanted to point out that number 3 here is asking you for how many calories is given up or lost. It's not asking for a temperature, and it's not asking for the specific heat of the substance. It is asking for the number of calories. Now, the most common symbol used for heat in the physical sciences is, well, you may not guess it. I wouldn't have guessed it. I didn't already know. It's a Q. So I'm going to put it up here. Q is equal to heat. I got to talk loud enough to make sure y'all can hear me. Q is equal to heat. That's most commonly given in the units of calories or joules. So when these problem number 3 is asking you for heat, it's when you use a formula to calculate the heat based on something that's already known, which is the mass of the substance You need the mass and the specific heat. I'm just going to use a big capital S for specific heat. I guess I could put SH and then put parentheses around it for specific heat right there. Okay? So you have to already know the specific heat of the substance. You have to know its mass. And the other thing you need to know is its temperature change. Well, it gives you that in the problem number 3. It gives you the temperature change. It says 56.7 to 25 degrees Celsius. So a decrease in temperature. And so that would be times a delta T here. Okay, so that formula right here allows you to calculate the amount of heat that was exchanged if you know those quantities, mass, specific heat, and delta T. What is specific heat? More quantitatively, let's write out what specific heat is. I'm going to put it like this. SH is equal to, well, it's equal to the heat, which is a Q, divided by the mass of the substance times temperature change of the substance. Our example, you use water. That's a very easy substance to use as a reference substance. And if you do that, the specific heat comes out to be 1 calorie of heat. We'll take and raise the mass. Well, we'll take and raise the mass of 1 gram, 1 degree Celsius. The specific heat of water is defined from that right there as 1 calorie per gram per degree Celsius. Okay? 1 calorie per gram. That says 1 gram of water requires 1 calorie to go up 1 degree Celsius. Okay. That was the original definition of the calorie, is the amount of heat required to raise 1 gram of water 1 degree Celsius. Okay? So, that's the definition of specific heat, is heat over mass over degree Celsius, or heat per gram per degree Celsius. Okay, now, back to the problem. I'm not going to do problem number 3 here. All you need is this formula right here and the specific heat of iron to do problem number 3. And then the specific heat of water, you can plug it in right there as well, and you get the value for that. What I'm going to show you is number 4. That's the big one. And so if you get number 4, then that's a nice chunk of points for you right there. Now, it says it's a 300-gram sample of glass. Okay. So all we got to do is come up here and we put in, I'm going to put it in like this. The mass of the glass is 300 grams. 300 grams, okay. And the specific heat of the glass. We don't know what the specific heat of the glass is. That's what you're trying to find in this problem. You're trying to find the specific heat of the glass. So we've got specific heat of the glass, which is unknown, times the temperature change of the glass. Well, what is the temperature change of the glass? It goes from 76 degrees down to 27 degrees. Degrees down to 27 degrees. That comes out to be 49 degrees Celsius. All right? But we need the specific heat of glass. That's what the purpose of the problem is to find the specific heat of the glass. So in order to do that, we need Q. And Q comes from calorimetry, okay, or we can figure it out from calorimetry. You can see that with these unknowns, or you can see this right here, this top equation, you rearrange it and you get this equation right here, okay? So you plug in right now everything that we got from the top equation. We don't know what Q is. Okay, so we just put Q, but we do know what the mass is. We'll put 300 down here, 300 grams. And we know what the temperature change is. It's 49 degrees Celsius. but we don't know what Q is. If we can figure out what Q is, then we can calculate the specific heat of the glass. All right, so all I did was take this top equation and rearrange it or solve for SH, the specific heat. So that's very simple math right there. Now we need a way to figure out what Q is. What is the heat that was exchanged? Well, it came from the hot glass. You read this problem, a 300-gram sample of glass was at a high temperature of 76 degrees Celsius. And then it was placed into the calorimeter, which we're going to do in the lab with metal samples in a minute. And it was cooled down to 27 degrees Celsius. Okay? Now, the way we get Q is using the idea of the heat that came out of the glass goes into the calorimeter, or into the water inside of the calorimeter. And it stays in there long enough for us to measure everything in terms of temperatures that we need. So let's look at this. The Q, keep in mind, that's the heat that came out of the glass and goes into the water in the calorimeter. It is equal to, well, it's the same thing up here, but we don't have the specific heat of glass, but we do have the specific heat of water. Now, you need to be careful because we're talking about the water now. And so you need to use the values for the water down here. You say, okay, the water is, from the problem, it says how many grams of water? 1,000 grams. Okay? 1,000 grams of water. And the specific heat of water is, well, I just told you a minute ago. Anybody remember? It's 1 calorie per gram per degree Celsius. So you put that in 1, keep some significant figures there. 1 calorie per gram per degree Celsius. That's the specific heat of water. That's the mass of the water. Now we need the temperature change of the water. Well, the water went from 27 degrees down to 23.9 degrees. So 27 minus 23.9, that's the temperature change of the water. And that's a small temperature change if you think about it. That's only a few degrees, whereas the glass went from 76 down to 27. It went 49 degree temperature change. But the water just goes through, what is that? 3.1 degree temperature change? 3.1 degrees Celsius. That's all this is. So that is an important observation because water can absorb a lot of heat or release a lot of heat without changing temperatures very much. That's an important property. You refer to that as a high heat capacity of water. As opposed to glass, well, from the evidence here, we're talking about the same heat absorbing, or in this case, giving off the same amount of heat. It goes through a 49 degree temperature change. A lot bigger temperature change to give off the same amount of heat as opposed to 1,000 grams of water. It only goes through a 3.1 degree temperature change to receive all that heat. So water is high heat capacity compared to glass, which is a much lower heat capacity. That's the same with many materials. Very few materials have a heat capacity or a specific heat as high as water. And so all the metals, their heat capacities, remember I told you a second ago, aluminum was 0.2 something and copper is 0.09. Well, water's specific heat is 1. 1 compared to 0.2, 1 compared to 0.09. Water has a whole lot higher specific heat, or a whole lot higher heat capacity, meaning that it takes a lot more heat to cause its temperature to change. It's good at storing heat. That's an important conceptual idea to get locked in your mind to understand this material. Okay, back to the calculation here. It's very simple. We have the heat that went into the water right here. It comes out to be, well, we don't even need a calculator for this. Do you need a calculator for that? I don't think you need a calculator. Well, you got 3.1 degrees times 1. Well, that's 3.1. 3.1 times 1,000 is 3,100 degrees. So Q is not 3,100 degrees. It's 3,100. Well, let's look at the units here. How does this work out? Grams multiplied by or divided by grams is canceling, so the grams cancel. Celsius times Celsius over here, that cancels, and that leaves you with just calories. That's the unit of heat. Okay, so you got to do your units correctly. Make sure you keep track of those. So 3,100 calories. And this has two significant figures, just the 3 and the 1. Remember, if I put a decimal place there, then you could say it has 4 significant figures. But in physical sciences, if there's no decimal place shown, then you don't count trailing zeros as significant. Okay, so 3,100 calories of heat went into the water from the hot glass. Now, what do we do? Well, you can take this result, because that's the amount of heat that came from the hot glass, and you can put it up here into this equation for a specific heat of the glass. We already have the mass of the glass. We already have the temperature change of the glass. All we need is the Q, the heat that came out of the glass. That's what we just now found. So I'm going to write it in as 3,100 right here. All right? 3,100 calories. Well, that's it. If you plug that in, you calculate the specific heat of the glass from your experimental data. So 3,100. I'm just going to hit 3,100, and then I'm going to hit divided by 300, and then I'm just going to go straight through and hit divided by 49, and then hit equals. What do I get? 0.21. All right, 0.21 is the final answer for this problem, 0.21. We need the units on that. Running out of space here. The units is going to be, I'll just rewrite it down here real quick. Units are going to be, the units are 0.21, well, it's units of specific heat. Calories over grams over degrees Celsius. So you put calories over grams per degree Celsius. That is our final answer right there for the specific heat of glass from the example's experimental data. Now, the example problem also says to calculate the percent error. Okay. Keep in mind, if you have any questions about any of this, please put them in the comments down below. I will do my best to go through and answer those as they come up or as soon as I can. And of course, you can also email me any questions that you might have about this. Okay. Now, this last part is a pretty standard calculation you do all the time for labs, because you're going to get your experimental result and compare it to other people's experimental results, or compare it to the accepted value, which is other people's experimental results that has been accepted as the accurate, true result. So in order to do that, a common way is, of course, percent error. So this is very useful. You need to know this for many different labs coming up. It's very easy. You just plug in. The way I like to do it is your value from your results. So in this case, we got 0.21 minus the known value. Well, the known specific heat of glass is 0.20. Okay, that's the accepted value. Now, you don't have to worry about units on this, because what you do next is divide by the known value, 0.20. And if you take units of the top and divide by the same units in the bottom, that cancels all units. Okay, that puts it in a ratio, a simple ratio. So when you do that, finally you take that ratio and you multiply it times 100. And that, you could say, is adding on the percentage unit. Okay, so you could say it's times 100. So you take, you don't hit the percent button on your calculator though when you do this. You just hit times 100. All right. So this comes out to be 0.01 divided by 0.20, and that equals what? Oh, well, I'm sorry. Times 100. That equals 5%. You only get one significant figure on this, all right? Whenever you do this subtraction, you come up with 0.01. That's just one significant figure. That 0 right there isn't significant. Leading zeros are never significant. So there's a 5% error according to the results that we got here. Any questions? If there are any questions, please put them in the comments section below. All right. Now, next up is to go to the lab and do the experiments. So, Well, walking down the hall, giving you all the full effect to go to the chemistry lab. What's this on the board, on the hall, in the hall? The joke of the day. Now, this has been actually on the wall here for a long time, months, but it seems particularly fitting under today's circumstances. What should you do with a sick chemist? Well, bury him unless you can cure him. I think they left out one option which we all know about. Quarantinium. Is there an element named quarantinium? You might want to check that out because quarantinium. Alright, this is the chemistry. A little out of season there, but hey, it's still nice. No food or drink in the labs. You all should know that. And here we go. Lovely looking lab, don't you think? Alright, I think I got everything needed for the lab for the most part. First thing is a beaker of water. Well, got to put the water in here. Don't need much water, just enough to submerge our sample metal. For the first metal, well, since I talked about it in the classroom there, let's do aluminum first. This is a nice little cylinder of aluminum. I'm just going to put it on the hot plate here, and I'm going to turn the hot plate up onto high. There we go. Now, it shouldn't take too long to boil because I didn't use a lot of water. You just need enough to submerge the aluminum in there completely. And so I'm just going to put that in there gently. It's not hot yet, of course. So there we go. Now I'm going to move it from here on out. I'm going to move it with a nice pair of tongs for moving the hot stuff. So I'm going to have to get this metal out of here after it gets up to a nice boiling hot temperature, which everyone knows, at least they should know, that water boils at 100 degrees Celsius. So I'm going to put that in there just to confirm, I guess, what the temperature of water boiling is. All right. In addition to this, what am I missing? I'm tempted to give bonus points if you guys can think about what I'm missing. That's right. Safety goggles. Don't forget, safety first. Now, this water has gotten up to, well, only 39 degrees so far. It's got a ways to go on that temperature. In the meantime, I'm going to be going over the rest of the supplies that we need here for this experiment. We got two, well, let's look at it. There's one coffee cup, two coffee cups, double stacked. That is super insulated. This is the basis for our calorimeter. But not only do we have two coffee cups double stacked for extra insulation, we have a cardboard lid with a hole in it. That is pretty sophisticated right there. I know, try not to be too amazed. Now, in case that's not good enough for you, the final level of advanced technology is the thermometer. Put it in the hole. And that right there is our calorimeter. But it's not standing up. Why isn't it standing up? Well, it's obviously top heavy, and what am I going to do in order to make it usable? We need to put water in the calorimeter. And like we showed in the classroom again, in the example problem that we went over on the board, how many grams of water did they use? 1,000 grams. I'm not going to use that much water. The directions, if you have read through those directions, say use 100 grams, and I always say use 75 to 100. I'm looking for a nice graduated cylinder. There, I found it, 100 milliliter graduated cylinder. That allows us to get 3 significant figures if we measure below 100 milliliters, which is good to have 3 significant figures. In our volume measurement, we need to know very precisely how much water is in this calorimeter in order to get good calculations to get the specific heat of the metal, in this case the aluminum. So I'm going to fill this up to between 75 and 100 milliliters. I like to get less than 100 because then it's easier to change the temperature of the water. A bigger temperature change inside the calorimeter is easier to measure and get better results. So if you put 100, you can still get okay results, but I like to put around 75 or 100. So let's see here. All right, I'm going to measure this, and you can tell me if you agree here. Well, it's got some bubbles in there. The bottom of the meniscus says 79.8. About 79.6, 79.8. Now let me see if y'all can read this. Let's see. I try to hold it steady. It's kind of hard to hold it steady, but 79.8 is what I'm going to go with. Yeah, well, maybe a little bit less than that. Let's go with 79.6. So write it down on your paper. 79.6 is the volume of the water. Okay, so let me show you where to write this down. Let me write it down here. Volume of water is 79.6 milliliters. See that? That's the volume of water, 79.6 milliliters. Now what's right below that? Mass of water. Mass of water. Now do you know how many times people I see in the labs, they wrote down 79.6 milliliters, or they wrote down a volume, and then they say, oh, mass of water. And then what do? They pick this whole thing up and then go over here to the scale and they put it down on the scale and they say, what? That's not right, because that includes the mass of it. You don't even need to measure the mass of the water. What did we learn from our density labs? That the 1 milliliter of water equals 1 gram of water. So 79.6 milliliters of water equals 79.6 grams of water. You don't need to measure it on the scale. But people always get that mixed up sometimes. It's just, you know, one of those things that drives me bonkers, because that means they obviously didn't understand the density lab that we just did last week. So 79.6 grams of water. All right, now you can see obviously that our water is boiling here, and it could be boiling away the whole time. My thermometer is looking at, well, right at 100 degrees Celsius. Okay, 100 with 3 significant figures is good enough for me. Now, it might read a little bit lower than that because it's not immersed as much as it's supposed to be in order to get the most accurate temperatures. But in this case, it's good enough. So, next thing that we need is the, well, I left out, we got to fill in the mass of the metal right here. So let me turn on my scale here and give you the mass of the metal. All right, here's the mass measurement. Should have done this before heating it up, but I took it out of the water so that we can measure the mass of it real quick. And it's 17.053 grams. So let's write that down. 17.053 grams. Okay, don't forget your units. All right, let's put that back in the water. Now, it needs to come to equilibrium at 100 degrees so that we will know the temperature of the hot metal, right? Because that's what we need for the calculation, is the temperature of the hot metal. Well, the metal is now in equilibrium with this boiling hot water. And the water is at 100 degrees Celsius, so we know the metal is at 100 degrees Celsius. So let's put the 79.6 grams of water into our calorimeter. All right. And we know that's initial temperature is what we also need to know for this water in the calorimeter, because we need to know the temperature change of the water in the calorimeter. We don't need to know the temperature change of the water, you know, boiling. We just know that it's hot water at 100 degrees Celsius, and the metal is at 100 degrees Celsius. So the initial temperature of the calorimeter is room temperature. Tap water should be about the same as room temperature. It looks like it's, well, 24. A very important part of this lab is reading the temperatures to the maximum number of significant figures, which is the 10th of a degree Celsius. You can estimate in between the smallest marks to get to the 10th of a degree, which makes it 23.5 or 23.6 degrees Celsius is what I'm looking at here. Let's see if y'all can agree. Okay, there's the scale, 20. Whoa, it's hard to hold steady. That last significant figure. That last significant figure is an estimate in between the smallest marks. 23.6 is what I'm going to say. Okay, 23.6. That's the initial temperature of the water inside the calorimeter. Now, the big step here for the experiment is transferring the hot metal into the calorimeter, putting the lid on there and swirling and measuring the temperature change every 15, 30, 60, 90, 120 seconds, as it says on the data sheet here. Right? Under the initial temperature of water, that's what we just measured. Didn't we say it was 23.6? 23.6 degrees Celsius. So you see right there, 23.6 degrees Celsius is the initial temperature of the water in the calorimeter. The temperature of hot metal is, well, I'm going to put it as 100.0 degrees Celsius is what it's reading on the thermometer here. I don't want to bring the camera over this boiling water. It'll get all fogged up and stuff. So that's the temperature of the hot metal, 100 degrees Celsius. Y'all see that okay, I hope? All right. Well, whenever it says right here, the maximum temperature of water, that is inside the calorimeter after I make the transfer into the calorimeter. So this is the big critical step here, is transferring it in here, putting the lid on there smoothly, and then measuring the temperature change. Now, it says 15, 30, 60, 90, 120 seconds. And I don't have a separate timer. What do? I'm just going to measure it, and when the temperature stops rising, that's what we need, is that maximum temperature. Okay? Maybe I can count. That's too boring. Here we go, transferring it. Boom. Put the lid on there real quick, and swirl. All right, see, that was the critical part. And going up, it's up to 25 degrees Celsius now. Swirling, swirling. It's up to 26 degrees Celsius now. So we've already gotten a couple of temperature degree units. Rising, it's up to 26.5. This is not a very good lid. I'm not happy with this lid. That's a source of potential experimental error right there. Okay, and now it's up to 26.7 or so. I can maybe see that. It's probably lost some heat to the surroundings because we don't have a very good lid, and I'm swirling it a lot. Now it's up to 27 degrees Celsius, 27.0. See that, 27.0. You see that good? Man, that's hard to see, huh? I'm sorry. Yeah, can't get focused. I'm just going to have to take my word on it because I can't get focused on it. Alright, well, 27.0 is still what it's on. Sorry, I can't get focused good. At least not when I'm doing it that way. I bet if I brought the camera over here, I can get focused on it good. There we go. All right. So we're interested in the maximum temperature of the water inside the calorimeter cup. And 27, I'd say it went up a tad bit to 27.2 or 3. Okay. So that's about it though. 27. Let's say 27.2 is the maximum temperature that it went up to. Okay, that's what I'm writing down. 27.2. 27.2 degrees Celsius. That's the maximum temperature change, or the maximum temperature that the water went up to, 27.2 degrees Celsius. Okay, well, that is all the experimental data that we need for this lab, for this one trial. Now, in the regular lab meetings, you'd be required to do at least 2 trials. Either repeat with the same metal or do a second metal of a different type and see if you get good results for that second metal. So what I'm going to do is a second metal real quick here, see if I get good results for that one, and give you guys the results from the second metal trial, and you can do the calculations for the second trial as well. Now I'm going to put this into fast motion for you so you don't have to watch every single thing as slow as we did for this first trial. So let's get to it. Right, now that is the experiment the second time around, and the only thing left is the calculations now. So a couple things that I'll give you, of course, here in case you had any doubts. We need the change in temperature of water, change in temperature of metal. Now on this set of data, this second metal that we did is, or was, brass. So we can write that down. Brass is practically, or very close to copper in terms of its specific heat values when you look them up on the table. But this is brass, okay? And so I'm going to write that on my data sheet so you won't forget, hopefully. Whenever you're doing your calculations, you'll know what to compare with for your percent error calculations. And then the first one that we did was aluminum. All right, so writing that down. So here is the aluminum data that we got at first. Okay, and here is the data for the brass. All right, now what you need is the change in temperature of water. That would be inside the calorimeter. That is what we are interested in. What is the temperature change inside the calorimeter when we had that heat trapped very nicely and we're measuring the temperature very carefully. So that's going to be from the initial temperature of the water, 24.3, up to 29 degrees Celsius for this second example of brass. Okay, you guys see that? So it goes from 24.3 up to 29 degrees Celsius. So that temperature change is, what is that, 4.7 degrees for the temperature change of water. Now you see why we needed to measure to the 10th place. If we didn't estimate that final temperature on the thermometer in between the smallest marks, we wouldn't have been able to get that 0.7 degrees, 4.7 degrees Celsius temperature change of the water. We would have only had one significant figure for the water's temperature change. Okay? We need two significant figures for the change in temperature of the water so that we can get two significant figures in the specific heat of the metal whenever we go through all the calculations. So now we have two significant figures for the temperature change of that water. And then we need to change the temperature of the metal. All right? So the metal goes from 100 degrees Celsius down to 29 degrees Celsius. So the change in temperature of the metal is just 100 minus 29, which of course is 71 degrees. So 71 degrees Celsius is change temperature of the metal. Now you should be able to plug in your numbers to the formulas that we gave on the board and the ones that are written in the handout and do all the calculations and all the questions. All right, so I leave it to you guys to finish up with all of the reflective exercises, but even more importantly is to make sure, so on your trial 1, we did aluminum. Okay, we did aluminum for trial 1. Make sure that you go through, you do the change in temperature of the water for the aluminum, you do the change in temperature of the metal for the aluminum, just like we did a second ago, and then you come over here, and you can write the calculation down here, okay, for the specific heat. That's what, when you turn the page, you look up here, it says determination of specific heat. That's talking about determination of specific heat. For us, it's going to be aluminum. Okay? Determination of specific heat of the aluminum. That's from the previous set of graph or data. Okay? Then you turn the page again, and it's determination of specific heat. Well, that's where the brass calculation is supposed to go. Of course, you can calculate it down here, the specific heat of the brass. Okay? You can calculate the specific heat of the brass down here if you want to, because all the data is right there conveniently for you to write into the formulas. And then just rewrite it over here so that I have it where the intended spot is, the blank is for it. And same with the aluminum. You can write it down here, the calculation, write out your whole calculation down here, and then put it over here as well, just so you make sure that I don't miss it whenever I'm going through and grading everybody's papers. All right? So that's the whole experiment. I hope you enjoyed this. I hope you learned a lot. Thanks for watching, and let me know of any questions in the comments and or emails, and see you next time.